Okay, hi everyone who has joined us today. We're going to give it just one more minute for everyone to get their audio set up, and then we'll kick it off. So. Okay, it's 11:01, so I think we'll get started, or 11:01 here in Mountain Time in Colorado. So good day, everyone, and welcome to this Global Power System Transformation Consortium, or GPST webinar, where we will discuss, as the title notes here, the impact of inverter-based generation on bulk power system dynamics and short circuit performance. We have Priyan Porbek and Gary Kovut here with us, who I will introduce a little later on. This webinar is presented by the GPST's Pillar 4 lead organization, IEEE, and the IEEE Power and Energy Society, as well as on behalf of the North American Electric Reliability Corporation Task Force. My name is Isabel McCann, and I am the GPST Consortium Interim Secretariat Communications Lead, based out of the National Renewable Energy Laboratory in Colorado, and I will be your moderator today. So with that, I am going to cover, before we get started, just a few quick housekeeping items. We are holding this event on WebEx, so if you would like to adjust your view, you can do so by selecting the layout options. If you hover over the top right of your WebEx viewer, you'll see that option come up, and you can choose any one of the layouts you prefer. Down here at the bottom left, you can kind of see what those different views look like, or will show you. If you have any audio issues, please try checking your audio outputs and the volumes. You can also try switching the mode you joined audio. So if you joined by computer audio, you can try dialing in by phone or vice versa. We will hold time at the end of the presentations for Q&A. Please use the Q&A function, which is distinct from the chat. Please note that it is distinct from the chat. And please ensure that you have selected all panelists to send your question into, so that we may all see the question. If you send it to the host, it's just going to come to me. And I can share it, of course, with Gary and Priyan, but please do try and select all panelists so that all of the panelists can see your question to address it there at the end. And please feel free to send in your questions at any time. We will address it at the end, but you're welcome to send them in at any time. You don't need to wait till the end necessarily. Finally, we are recording this webinar, and that we will have it available on the GPST website and our YouTube channel once it's concluded. Now, ahead of our technical presentation, I will provide just a brief overview of the GPST Consortium. You can see our logo here, as well as the logos of our many partners. So what is the GPST Consortium? It is a new initiative recently launched. In fact, we did just host a launch event as a side event to President Biden's Climate Summit last week, where we had CEOs and the U.S. Energy Secretary Jennifer Granholm, as well as the UK Energy Secretary, or BEIS Secretary Kwasi Kwarteng, join us for our launch event. So it was recently launched with many partners from around the world, with a very targeted focus on support and collaboration with global power system operators to research and implement cutting-edge technology and solutions to bring very high levels of renewable energy and complementary technologies onto the grid. The GPST's work is spread across 5 key pillars, which you can see here on the right-hand side. Our Pillar 1s of System Operator Research and Peer Learning, led by the Energy Systems Integration Group. Pillar 2, System Operator Technical Assistance, led by the National Renewable Energy Laboratory. Pillar 3, Workforce Development, led by Imperial College London. Pillar 4, Localized Technology Adoption Support, led by IEEE. And Open Tools and Data, led by VTT Finland. So our partners do include several leading energy system operators who we work with at the CEO level, including California ISO, National Grid in the UK, AMO in Australia, EirGrid in Ireland, and an EnergyNet in Denmark. In addition to our founding system operators, the GPST is also composed of a core team of technical institutions, who you can see on the bottom left here, who come together to define the direction of the consortium, lead on our specific topical pillars, and regional activities. Finally, we are partnering with developing country system operators such as PLN in Indonesia, ESCOM in South Africa, COES in Peru, to support them in advancing power system transformation, as well as having them help lead on peer learning in those regions. So if you would like to learn more about the GPST, you can visit our website at globalpst.org. You can stay updated with news and events from the GPST, such as events like this one, by joining our mailing list on our Get Involved page. There you can also engage in our regional peer learning or indicate interest in engaging in our regional peer learning networks and pillar groups by indicating which pillar you're most interested in, or if you're interested in all 5, you can select all 5. And finally, you can always reach out to us by sending us an email at globalpst@nrel.gov. So with that, I will introduce our speakers today. So we have on the line with us Puyan Porbak, the President and Principal Consultant of Power and Energy Analysis Consulting and Education, or PES, PLLC. Previously, Puyan worked with GE Power Systems, ABB, and EPRI. He is a registered engineer in both Texas and North Carolina and is a fellow of both IEEE and SIGRI. We also have Gary Kobit, an electrical engineer with the Tennessee Valley Authority. Gary oversees TVA's phaser measurement system and advises on system operations. He's also a member of the IEEE PES Power System Relaying and Control Committee. He is a registered engineer in the state of Alabama and an adjunct professor in the electrical engineering department at the University of Tennessee at Chattanooga. So with that, I will go ahead and hand it off to Puyan to get us started with our technical presentations. Puyan, take it away.
Thank you very much, Isabel, and thank you, everyone. Good morning, good afternoon, depending on where you're at. And I assume you can hear me okay. If not, let me know.
We can hear you. Great.
So again, as Isabel very kindly said, we're here to present on this subject, which is reviewing this IEEE NERC task force that Gary and I had the privilege of working on a couple of years back. And we'll talk about the task force. The report is available on the PES Resource Center to all PES members, and we'll also touch on some of the activities since that time that are going on in the industry, and then get to Q&A. So if we just go to the next slide. So the report was published in July 2018. As mentioned, it's on the PES Resource Center, and it discusses basically some of the potential concerns and opportunities with inverter-based resources being connected to the bulk electric power system and sub-transmission system, and then identify some broad industry activities needed to address some of these issues. And as I said, some of that has already gotten going. It is going at the moment, and we'll touch on some of those. And then it identified some gaps as well. And again, once again, those are being addressed by IEEE and other working groups and standards that we'll talk about here in a minute that have started since that time. So if we go to the next slide, the motivation for this task force was some of the events that happened in 2016-17. Not going to go into the details. Many people may already be familiar with these. There were some large events both in California and in other places in the world like South Australia, where there was sudden, loss of renewable generation, and system operators got all excited, and so we had to take a deeper look at what was going on, and that kind of was the motivation for this task force to take a closer look at some of these inverter-based resources. So if we go on, the task force was formed in 2017 through a MOU, a Memorandum of Understanding between PES, IEEE, and NERC. And again, the main driver was looking at these large portions of inverter-based generation coming onto the system. How does that impact short circuit levels? How does that impact system inertia? How does that impact just dynamic performance as a whole? What are the sort of things we need to be looking at? And again, maybe I jumped into this just to explain, sure everyone's on that same page, but just to ensure when we say inverter-based resources or generation, we're talking about resources that are connected to the grid through a power electronic interface. So those tend to be, in today's world, either wind generation, solar PV, or battery energy storage, or sometimes a combination of all, hybrid plants. So those are typically the kind of resources we're talking about here. So renewable, in the case of wind and PV, there's variability in the source as well. Battery obviously is a solid source. So if we move on, so the task force was made up of utility members, vendors, consultants, NERC and IEEE PES, and the two kind of PES committees that were represented mainly with the Power Systems Relay and Control Committee and the Power System Dynamic Performance Committee. And if we move forward, and the list of members was given there, though they're small, you'll have to get the report to read all the member names and likewise table of contents, but we'll go through this here briefly in a second. So if we keep moving forward to the next slide. So the first section I'll cover is the large system dynamic performance issues, which is kind of the first half of the report, if you will. And then I'll hand it over to Gary to cover the second section, which is the short circuit and protection issues. So if we move on, here are kind of in bullet form on the left-hand side, all the kind of topics that were covered in the report. I'll just talk about them high level briefly, and we'll give some examples. And then in the Q&A, if we want to go into specific questions, we're happy to do that. So we discussed in the report, obviously, things like voltage control, reactive support that you would expect from inverter-based generation, frequency response and frequency control. What are some of the issues related to low short circuit levels on the system, control and grid interactions between the controls of the power electronics and the grid, like in the case you have series compensation or if you have other devices close by. What are some of the issues around planning processes, around modeling of these devices, operational economic issues, and honestly, in that regard, we basically say in the report that economics is outside the scope of what we discuss here. This is a very technical report, but just to state that. And then some basic other issues were discussed as well. Many of the past and existing groups within IEEE, NERC, and WEC and IEC have been addressing these. Some of the gaps that we identified are now being addressed by new activities that started last year. The most notable is the IEEE P2800 standard draft working group. That working group is led by Jens Boehmer at EPRI, and it's a working group bringing together a draft for an IEEE standard. We'll talk about it briefly later, just at this point, just mentioning it. So if we move forward, so two of the most important gaps in terms of voltage control was that, and I'll show you examples here of some recent tests of actual plants. Renewable generation, inverter-based generation can definitely do voltage control, can do it very well, very fast. The gap at the time of this report was that, you know, some of these definitions I put here on the right-hand side, automatic voltage control. What do we mean by dynamic? What is the performance expected for a SAG? What's central versus local, control? What about distributed IBR? All these things lacked clear definition, so you would find, maybe different projects, different entities were doing them subtly differently. So the gap here was due to this large displacement of conventional generation you could get into a scenario of not having adequate voltage support or reactive support if the controls weren't done in the appropriate way. So the real gap was, well, how do we define these things? And again, as I said, the P2800 is addressing that. We'll talk about it in a second. If we go to the next slide, one of the other issues around this whole control of voltage and reactive power was this issue here. On the left-hand side, you see a simple diagram. It's showing you that an inverter or a power electronic converter is basically a current-limited device. So if we think about the y-axis being reactive current and the x-axis being active current, then it's just a circle on this, XY plot. And obviously, the right-hand side of the circle is when you're putting active power into the grid, so like a wind plant or a PV plant. The left-hand side is if you have a battery, you can also absorb power from the grid. But it's essentially a circle. Now, the issue was, again, because of no clear definition in, shall we say, globally, of what we expect in terms of reactive support, some cases people would do what you see on the right-hand side drawn as a yellow triangle, where they would allow a constant power factor from full load to no load. So you only get the limited reactive capability you see in that yellow triangle, whereas you have more available. So at the very least, you should be able to get what's shown by the green box, where you get a constant level of reactive current through the operating range of the device. And again, I put Q and P there. These are really currents, so the actual Q will also vary as a function of the grid voltage. But still, the concept is, if not properly defined, you may end up limiting the device beyond what you really want to, if that makes sense. So the gap right here really was having a well-defined, what do we expect in terms of reactive support. So if we go to the next slide, in terms of frequency response, so on the right-hand side, you see what you would expect in a typical scenario on a grid when you have, say, loss of the largest generator on a grid. Your frequency being, at least in North America, at 60 hertz, you lose some generation. Initially, you have that kind of darker, red or pink area where you have a decline in frequency that's driven by the inertia of the system, so the rate at which frequency drops. Then you get to that kind of nadir point C, and at that point, your turbine governors, conventional governors, will start to kick in, start to provide frequency response, primary frequency response, and so the curve turns around, frequency starts to pick up, and then finally settles down, stabilizes in that green area, region of new equilibrium. And then finally, in that purple area at the end, you have things like AGC, secondary control, come in and bring the frequency back up to 60 hertz. And the question is, can IBR or inverter-based resources do this? Yes, but again, you need to be able to define it, define the performance you require, and how you want it done. And I'll show you examples where it is actually done. So if we go to the next slide, so here's some examples to kind of illustrate that these things can actually be done. So on the figure here, what's shown in blue is measurements. What's shown in red is actually simulation using standard generic models in one of the planning software tools. And the top plot is the plant's total megawatts at the POI. This is a wind plant. The plot in the middle is the reactive power at the point of interconnection, and the plot down the bottom is the voltage at the point of interconnection. And the event here was a large shunt capacitor on the grid was switched, and you can see that when it was first switched at the beginning, you had a sudden jump up in the voltage at the POI. Then you can clearly see that immediately the turbines, there's a little spike down in Q, that's the turbines immediately reacting, pulling Q down, and then the plant controller as a second layer of control slowly brings the voltage back to where it started. And then when the capacitor switches again, so we switched it in, now we switch it back out, the opposite happens. So you can see clearly that you have both very fast control given by the turbines and then a slower tier control for vernier control that's at the plant level. So it can be done. It's not a problem. And if we go to the next slide, here's another example where you have a larger plant. There's two, if you will, large collector systems coming onto two substation transformers, and you have an overall plant controller, and you can see where we can give a reference step to the plant controller and very quickly change voltage up and down. No problem. And the current models can mimic all this, and they did in the previous example as well. And if we go to the next slide, here's an example of frequency control from a large wind plant. So in this case, I have to explain this a little bit. So let's just step back for a second. So frequency response, can it be done with inverter-based generation? The answer is yes. There is a caveat, and that's the second bullet point. There is lost opportunity cost associated with providing under frequency response, or in other words, providing frequency response when the system frequency drops. So particularly in the case of wind and photovoltaic generation. So let's explain that. So let's assume we have a wind power plant, and let's assume that at this point in time, there's enough wind incident on our plant for us to produce 100 megawatts of power. Well, we want to then produce 100 megawatts of power, because if we don't, we lose that opportunity because that wind may not be there an hour from now or 2 hours from now. So we want to produce as much power as we can at this point in time. That being the case, if there's an under frequency event, we have no room to move up because we're already producing all the power we can. In order to be able to have room to move up, we have to curtail the plant a little bit. And the plot on the right is a case where in this particular system, in this particular case, the operator had curtailed the plant because of other reasons, because of congestion on the transmission system, some other issues. They had curtailed the plant. So it just so happened that the plant was curtailed and the frequency event happened, and you see in the bottom plot the system frequency dropped, and you see in the top plot the wind plant responded and provided primary frequency response. And you can see with the red dashed line, we're able to match it quite reasonably with the standard generic models. The point is, if you want to do this all the time, there is cost to this because there's opportunity cost for keeping a wind or PV plant curtailed all the time. You're losing money and you're losing generation you could be putting on the grid. So to do the primary frequency response for under frequency events, there are commercial issues that may have to be taken care of in a market paradigm, and that's outside the scope of what we're discussing here. But from a technical standpoint, it's doable, and there you have it. And if it was a battery, well, it's of course always doable because the battery's got stored energy. And also, over frequency is always doable with wind or PV because you could always decrease power, right? So if we go to the next slide. So really, these were kind of high-level recommendations. We had some recommendations on how there's a need for good qualified definition of voltage control reactive support. Some of this was actually addressed by the NERC Inverter Resource Performance Task Force, and now is being further addressed by the P2800, which I'll mention in a minute. With the FERC Order 842 that came out actually in February 2018, a lot of these issues around frequency response were addressed, at least for the North American market. And in the FERC order, they say that capability is needed. They give recommended levels for droop and deadband, and they further clarify what we just discussed, that you do not have to carry reserve because there's opportunity costs associated with that, but you just have to have the capability to do it in the case you're curtailed. Now, if in some system it's identified that that reserve is necessary, well, that system will have to figure out a payment mechanism or a market mechanism to make that the cost associated with it addressed. Then there were discussions around the low short circuit level issues and protection issues, which Gary will cover. And then in terms of control and grid interactions, these tend to be very case-by-case specific. There is a PRC task force working on some of these, may have already completed their task. Again, for these kind of analyses, you really need vendor-specific proprietary three-phase models. They have to be addressed on a case-by-case basis. And if we move on to the next slide. So again, planning process, there's no single reference. These tend to be regional. From a modeling standpoint, the WEC Renewable Energy Modeling Working Group and IEC have put out a lot of standard generic models that are now, and certainly all the North American, starting to get into European planning tools, and they've been benchmarked and tested across the board. So there's a lot of solid standard models out there. And then, of course, there's always the vendor-specific models that you need for more detailed studies, and they're, of course, available. They tend to be things you have to get under NDA, though. And then operational economic issues, as I said, we discussed somewhat in the report, but really is outside the scope of NERC IEEE because they tend to be more commercial issues than technical issues. And if we move on, so just wanted to talk real briefly about these two recent industry events. One of them is the P2800. It's a standard. It has already undergone initial balloting. The balloting was closed April 10th. The public comments period, I think, ends next week. There is also a proposal for a new PAR, for a new proposed standard. So this is just a proposal right now to look at recommended practice for testing and verification of inverter-based resources. If we go to the next slide, just a high-level mention what the P2800 standard is on. I'm not going to read all this. Actually, if we go to the next slide, I'll leave that for people to read later. This is what the standard covers. And again, it's a draft standard. It's not yet an approved standard. It's just gone through initial balloting. And there are hundreds of comments which will have to be addressed. The standard covers all these things, really, that we just discussed, that the NERC task force had identified as gaps, to define reactive VAR control requirements, to define active power frequency response requirements, minimum requirements, to define minimum requirements for fault ride-through, for power quality, protection. It talks about the kind of models that are out there available, what are some of the measurement and data requirements for validating those models, and starts to touch on test and verification requirements, although those will need to be more fleshed out in this proposed second standard P2800.2. So if we go to the next slide. So summary, in summary, before I hand it off to Gary, modern IBR is certainly capable of extensive functionality. They can do volt-VAR control, frequency response, the whole 9 yards. In fact, they have a lot of capability. The key thing as an industry for us to figure out is to specify these kind of minimum technical performance requirements consistently so it is understood what's required of them. The draft P2800 is working towards that end. Obviously, there's still more work to be done, but it's working towards that end. In terms of what the future holds, you know, IBR have already proven in many systems they're capable of all these functionalities. So we just need to keep advancing the technology. You know, in recent years, and there are some of these already in systems that talk about grid forming inverters, which is the next phase of the technology. And so continued R&D is essential, and these technologies will advance. And I'll leave it at that and hand it off to Gary.
Okay, can you hear me?
Yep, we can hear you, Gary.
Okay, all right. Thank you, Isabel. Thank you, Isabel, for that introduction a second ago, and thank you, Puyan, for your comments on large system issues. And I'm going to cover the balance of the time with talking about short circuit performance issues. So let's go to the next slide. And these are the things that I'm going to discuss that are all addressed in the task force paper that, as Puyan said, is available in the PES Resource Center. We're going to discuss how the paper discusses how different relay elements respond to IBR current voltage, which is the nature of the response is different than conventional synchronous machines. There have been misoperations of negative sequence elements, of negative sequence directional elements that are documented, and the paper provides references to those. I'll discuss a little bit about that in just a second. Under frequency load shedding and the effect of lower system inertia and faster rate of change of frequency. That's an issue. Frequency tracking issues. Relay scheme impact, the paper goes through a little bit of detail on that, and some follow-up work by some Power System Relay Committee working groups that have completed their work recently go into that a little bit more. Impacts on short circuit studies, I'll talk about that. High source impedance ratio, modeling issues in short circuit programs, and then a list of NERC PRC standards that have been impacted, and I think there's still some work going on there. Next slide, please. The issue with IBR fault current. Now, the way that protection systems conventionally detect whether there is a tolerable condition or load carrying and an intolerable or a fault condition are by a few different, what Blackburn calls in his protective relaying textbook, he calls them handles. When a fault occurs, typically in a conventional power system, the voltage sags, decreases, the current magnitude increases, and the current phase angle becomes more lagging relative to the faulted phase voltage. And with conventional synchronous machines, that's how protective relays tell the difference. The voltage sags, the current goes up, and the current becomes more lagging. The issue with IBR is the fault current may not respond that way. The other thing about synchronous machine currents is that they become significantly higher, 5 or 6 times maybe what the load current is. But for IBR, most of the time the short circuit currents are limited to about maybe up to 120%. Now that's, you may get an initial increase in current up to 2.5 per unit, but only for a quarter to 2 cycles. But the IBR devices are protecting themselves from overcurrent, and so they reduce that current output. So there may not be as much difference between load current and fault current. And the fault current angles are essentially undefined, so we're not sure what we're going to get with those. And the other piece is that the sequence components, whereas for unbalanced faults, this is an issue for unbalanced faults, but IBR typically produce only positive sequence and negligible negative and zero. If you go to the next slide, This is a representation of an IBR in the 3 sequence networks. It's a constant current device in the positive sequence network, and no zero sequence current, so the switch is open on the far right, and then in the middle, whether you get negative sequence current or not is dependent on the control system programming. And so where conventional protection systems are depending on negative sequence current, there may not be significant negative sequence current for an unbalanced fault. Next slide, please. And so the reason that in a conventional power system that the fault current becomes more lagging is because the elements in the conventional power delivery system are primarily inductive. The transmission lines, the generators, the transformers are all primarily inductive. So when a short circuit occurs and the load is short circuited, then all you have left is essentially inductive elements. And the directional elements in conventional relays have been designed to operate on that principle. The negative sequence elements, in particular, compare the negative sequence current with the negative sequence voltage. And when I2 leads V2, those are the negative sequence quantities. By 90 degrees, a forward decision is made. Next slide, please. So this is just a sample system just to illustrate the point. If you look at bus L, which is in the lower right-hand corner, and breaker 10, which is on the line from bus L to bus H. The relay there that is just below breaker 10, and the boxes there, this is a single line representation of a 3-phase system. The boxes are circuit breakers. The breaker 10 on line 4, and then we have 2 fault locations, one fault F1 and one F2. And for a bus fault, we get a certain, of course, if it's a bus fault, if the fault voltage is going to go to 0, assuming a voltage fault. For fault F1, for a fault just on the line side of the breaker, the voltage on the faulted phase or phases will be identical to a bus fault. The difference is the currents. For fault F1, the current flows from bus L to the fault up. For fault F2, the current flows down through breaker 10 to fault F2. And what the relay has to decide is the fault forward or reverse? And so we have different polarizing methods that help the relay decide where the fault is. And so the issue here is discrimination. Next slide, please. And one way that this is done is with a negative sequence comparison. And I said this a second ago, but this is just to illustrate. The V2 is the polarizing quantity, and the I2 is the operating quantity. And when I2 leads V2 by 90 degrees, or plus or minus 90 degrees either side of that, then the negative sequence element can make a decision. Now, this decision is contingent on there being enough negative sequence quantity, voltage and current, for the relay to make a phase angle determination. If I have 3 or 4 amps secondary of negative sequence current and 12 volts secondary of negative sequence voltage, then the relay is going to be able to make that decision. But relays have directional element thresholds where you have to have, say, 1 volt of negative sequence voltage and a half amp or 1 amp of negative sequence current. In cases where the negative sequence quantities are below the thresholds, the relay cannot make a directional decision. And so with large penetrations of inverter-based resources, there is a possibility that there will not be enough negative sequence for a directional element to make the proper decision. And that has already happened in a couple of places in North America. And so this is an issue that the industry is going to have to deal with somehow. Now, another method of polarizing that is used, and I should say that the use of negative sequence directional elements for ground faults is widespread, and one reason that it is used is that it is immune to zero sequence mutual coupling problems. There are other methods of directional determining ground fault directionality, and one of those is zero sequence voltage and zero sequence current But if there is, say if you have a 500 kV line in parallel with a 230 kV line, and there's a fault on the 500 kV line, there will be a ground fault, that is, there will be, could be induced current in the parallel 230 kV line that could cause a misoperation for a zero sequence element. But with negative sequence directional elements, that's not an issue. So the industry's, my experience at least, is that the industry has been moving more toward negative sequence directional elements, but in cases where mutual coupling is not an issue, zero sequence could be used. And another way that zero sequence directional elements are implemented is with the use of transformer neutral currents. And one way that large concentrations of IBR are connected to a transmission system is through a transformer that is Y grounded on the high side and has a delta winding that allows the transformer to be a ground source or a path for ground zero sequence current. And that transformer neutral current can be a good source of polarizing current as long as there is not a significant mutual coupling issue. So just to say that that's another way of handling this. Next slide, please. Some other aspects of protection that can be affected by inverter-based resources: polarizing methods for distance elements that rely on memory voltage or cross-polarized voltage. If the fault angle relationships do not change significantly during a fault, if the fault current angle doesn't change significantly during a fault, then the polarizing for the distance element may not be as reliable. Next slide, please. Some other issues: faulted phase selection, fault location, fault detection. All these methods are based on conventional generator response during faults. So if, and this is typically it's called a voltage behind impedance model for the synchronous machines. If that is not true of IBR, then these phase selection, fault location, fault detection may not work as intended. And so in the next slide, we have a piece of the draft of the P2800 standard that Puyon mentioned. And as he said, the document's available for public review, but in a section of that document, one of the requirements is that for unbalanced faults, in addition to positive sequence current, the IBR shall inject negative sequence current with these characteristics, that it be dependent on the negative sequence voltage and also will lead the negative sequence voltage by the phase angles shown. And I left a footnote down there. It should say 90 to 100 degrees comma for full inverter-based IBR. There's a footnote 109. I forgot to take out the 109. I apologize for that. But there is a requirement for IBR to produce this negative sequence current such that the relays that are out there now will be able to actually tell whether there's a fault and determine fault direction. And on the right side of this slide, there's a table that specifies voltage ride-through requirements and the step response and settling time and that kind of thing. But the P2800 standard is the industry's, at least IEEE's, attempt at documenting requirements that utilities can use in their discussions with IBR so that the protective relaying that we have out there will actually work. Next slide, please. And don't need to spend a whole lot of time on this. Some of this becomes redundant. The phase and ground overcurrent elements, if the issue again is if there's not significant negative sequence current for unbalanced faults, or there's not significant changes between load current and fault current, then overcurrent elements may not be reliable. So in any case where you have overcurrent elements that are used for tripping, that's certainly a danger that the relay may not be able to discriminate between faults and load. Next slide, please. The same is true for distance elements that are supervised with overcurrent elements. Again, there has to be enough current for the relay to say, yes, there's a fault. Again, this becomes a little redundant, but you get the point. Next slide, please. Another issue is weak sources. So in a case where I have a transmission line between two strong sources, and I have a tapped connection of an inverter-based resource and, somewhere along that line, and there's a fault near one of the terminals, let's say that the actual impedance from location VC to the fault is only 10 ohms. But if these are the fault currents, what a relay that at location D, or where VD is located, the impedance that terminal measures will be magnified by the infeed from the strong source to the left at VA. And that relationship is given there, and the relay at VD will actually measure 260 ohms instead of 10 ohms. And so high apparent impedances for weak sources are another effect of inverter-based, or can be another effect of inverter-based resources. Next slide. Another area has to do with power swings and the rate of change of impedance, or the impedance trajectory, the rate of the swing change. So on the left, I have a couple of distance elements on a transmission line, and a stability study was done, and the impedance locus passes behind the terminal. And so for that particular terminal, out-of-step blocking would not be needed. On the right, at least part of that system has been changed, where conventional synchronous generation has been changed to inverter-based resources. And this is just an example, and you can see that the impedance locus now passes actually through the line, actually passes through zone 1 and zone 2. And so power swing blocking may very well be needed. It looks like it will be needed, at least in this case, due to the swing rates being changed. And this has to do with changes in inertia of the system. Next slide, please. And if you look at this, this is a test system that the Power System Relay Committee, Line Protection Subcommittee D, and Working Group D29 is actually studying these things. And this is a test system that they are using, and it uses a commercially available transient stability program. And so what they do in this case, where the up in the upper left, where it says open breaker at time equals 0.1 second, that circuit breaker, it's actually at substation Fur on the Elm line. So that disturbance is simulated, and then they observe the power swing at the Maple station on the Spruce line. And the maximum power transfer when the Fur Elm line trips, the maximum power transfer on the Maple Spruce line is exceeded, and you end up with an unstable power swing. The next slide shows two different results for different slip rates. On the left, the slip rate was 0.63 hertz. And in this case, there was one slip cycle. But on the right, with an increased amount of inverter-based resources in the same system, in fact, half of the inertia, so half of the conventional generation has been replaced with inverter-based resources, so the inertia constant is half of what it was. And on the right case, the slip rate has increased to 0.77 hertz, and two slip cycles for the same time period in the stability study, the transient study. Two slip cycles had occurred. And so in cases where the power swing blocking logic is looking at, in most cases, I think that's how power swing blocking works, is the time it takes for an impedance trajectory to pass between blinders. If those swing rates change appreciably, then it will require adjustments in the power swing blocking settings. So just something else to think about there. Another area, the next slide starts into the effect on under frequency load shedding, and this is an equation that can be used to estimate the rate of change of frequency in an area. So if I have an area that has 1,000 megawatts of import, and I'll show you what the system actually looks like in just a second. It's actually an 8,000 megawatt. For the example here, it's an 8,000 megawatt system with 7,000 megawatts of generation and 1,000 megawatts of import. The loss of that 1,000 megawatts of imports is going to cause a rate of change of frequency on the initial trip, and until the governors can respond, there is a danger of under-frequency load shed in the area. The next slide shows two different examples for two different inertia constants, total inertia for the system. On the left, there's the total inertia is 210, and the rate of change of frequency for that, I don't know the exact rate. I don't think I know the exact rate of change of frequency. I'd have to calculate it, but you can see the frequency decline, and there's a table on the next slide that actually shows the actual rate of frequency decline. But with the inertia, thank you. With the total system inertia of 210, the rate of change of frequency is 1.4 hertz per second, and with half of the system being inverter-based resources, 3,500 megawatts of conventional and 3,500 megawatts of IBR, the rate of change of frequency increases to 2.8, which is double. So if you go back to the previous slide, please, I apologize. I have those out of order. So the rate of change of frequency is higher, and the results are that on the left, based on that rate of change of frequency, you may shed about 800 megawatts in this sample system, whereas on the right, when the rate of change of frequency is double, you stand to possibly shed additional load. And so the whole idea here is that under-frequency load shed schemes may have to be adjusted to account for this. And the next slide just has for different percentages in that same test system. The next slide shows a part of the P2800 standard that requires that the rate of change of frequency will be less than or equal, or the IBR plant shall ride through and not trip for frequency excursions less than or equal to 5 hertz per second. So that's something that the P2800 standard calls for. I will note that the Australian event back in, I think, 2016, I can't remember exactly the date, but the Australian event, the Australian entity decided that they would set their limit for inverter-based penetration. Their limit is the rate of change of frequency can't be higher than 3 hertz per second in their system, is what I remember. So, and I will recommend a paper by the vice chair of this task force that developed this paper. Kevin Jones and some colleagues wrote a paper called "The Need for Faster Under-Frequency Load Shedding," and I highly recommended it. As provides a little more detail on this subject. Next slide. So frequency tracking is also something that is that can be affected here, where microprocessor relays are attempting to determine the system frequency. If the frequency is changing more rapidly, then you may lose frequency tracking, is the issue there. So that's another issue. Next slide. Synchronization is also a topic that is touched on in the working group of the task force paper. And the bottom line here is that the inverter manufacturer has to be consulted. There are a couple of industry standards, C50.12 and C50.13, that apply to conventional, synchronous machines, but for IBR, the idea of synchronizing inverters to inverters or groups of inverters to rotating machines, those synchronization requirements have to be discussed with the inverter manufacturer. And the next part of the paper talks about, on the next slide, talks about relay scheme selection, and these schemes are well known throughout the industry, and the details of the schemes can be found in C37.113. But the paper addresses, and then some further work by the Power System Relay Committee discusses some changes that may need to be made to different relay schemes. For example, permissive schemes may require weak feed echo. Blocking schemes won't require that. Line current differential is actually really good for inverter-based resources because it can operate for internal faults as long as one end sees is a strong source, as long as you have current above the sensitivity limits, I should say. And then some other things here about phase comparison schemes. More on that in just a second. The next slide talks about high source impedance ratio, and this is a sample system. And the idea here is that if you have very high source to line impedance ratio, for faults, internal and external faults, there may not be enough difference between the fault currents for an internal and external fault for the relay to discriminate between the two. In the sample here, the difference is only like 10%, less than 10% of, for an external bus fault and an internal fault, the difference is only less than 10%. So this is another issue, and so for cases where you have high source impedance ratio, there are times where zone 1 actually an instantaneous underreaching element cannot be set, and even pulling zone 1 back may not be. It may be to where you may have to pull zone 1 back to the point where it's almost useless. Pilot relaying on lines that have a high source impedance ratio is one solution for that. Line current differential is one form of pilot relaying that may work for that. There is a working group in the Power System Relay Committee D38 that is working on this issue. And I have a few more slides here. The next slide talks about short circuit study issues. Typically what protection engineers will study is all ties closed or all system intact, all generators online for setting instantaneous elements, for example, ground instantaneous elements. But now the case may be that we also need to study minimum generation to make sure that the fault detector settings are exceeded or overcurrent elements have enough quantity to make operational decisions, trip decisions, directional decisions, those kind of things. Otherwise, the elements may simply not operate. Next slide. The paper goes into three different sample system studies where conventional generation has been replaced with inverter-based resources. One study has 50% IBR where there used to be 100% synchronous. And the bottom line here is that very near those locations where there used to be synchronous generation, where there's IBR now, there, of course, and this kind of makes sense, is that you may have sensitivity issues at those sites. The further you get away from those and further more toward where the synchronous generation remains, there isn't that much of as much of an issue. But all these things have to be taken into account. So there are three different case studies in the paper, and I'll refer you to that for more details. The next slide talks about short circuit program modeling, and EPRI, along with Power System Relay Committee Working Group C24, did a lot of work on specifically on fault calculation, fault modeling, wind farm modeling in commercial fault calculation programs. And that work was completed last year, and that their paper report is available on the PSRC website. So what they do is they come up with a voltage-dependent current source model that can be used with either a table or models with different algorithms based on the control method. And so that report is available. Another IEEE Power System Relay Committee group in the next slide shows was Working Group C32. And this report was also completed last year and is available on the Power System Relay Committee website. It addresses the things that we talked about here about distance and directional element sensitivities, and provides recommendations, including the use of direct transfer trip from strong sources to IBR sites, and also the use of phase-to-phase undervoltage. to go along with distance and directional element schemes. Line current differential, of course, we said a minute ago, line current differential is an excellent scheme typically in these kind of systems. Directional comparison schemes, such as permissive overreaching and directional comparison blocking. The permissive schemes may need echo, weak feed echo, and possibly direct transfer trip. Another thing that their report mentions is that synchronous condensers provide a couple of different benefits. Of course, they bring their own maintenance challenges, being rotating machines, but synchronous condensers still provide inertia, being rotating machines, and also fault current independent of output. So that's something else that the industry may want to consider. And then there's a few other Power System Relay Committee activities that I don't have listed on a slide. There's another working group called C25, which is the protection of wind electric plants. The D29 working group I mentioned just a second ago, which is a tutorial on setting impedance-based power swing blocking and out-of-step tripping functions. And then D38 I mentioned, which is the impact of high source impedance ratio on distance relay. And then I'll also mention there's another IEEE guide that the Relay Committee put together called C37.246, which is titled The Guide for Protection Systems of Transmission to Generation Interconnections. And just a couple of pages in that guide mention setting considerations for renewable energy sources, but it's only a couple of pages. So these Power System Relay Committee activities are intended to help address the industry challenges. So C24, C32, D29, D38, and then this C37.246, along with what the IEEE is doing with IEEE P2800. And then last but not least, I have a slide on, here are some, the next slide is on possibly affected NERC standards. NERC was involved in the writing of this paper, this task force paper. And so these are some of the protective relaying and modeling standards that will be or have already been modified to include the effects of inverter-based resources. So, and then in summary, on my last slide here, so the summary of short circuit issues, one of the big issues is sensitivity issues, that there will be enough fault current with the right phase angle relationship for protection systems to discriminate between faults and load, and transmission system protective scheme changes that will be necessary to accommodate potentially weak sources when it comes to the fault current. And line current differential, directional comparison schemes with possibly direct transfer trip, that kind of thing. The best case is that we have adjustments to the inverter-based resources themselves, and that's what one of the things that P2800 is trying to do, is require a certain characteristic negative sequence response for unbalanced faults, along with changing the transmission system schemes so that we can actually detect faults reliably. Loss of system inertia effects, and we talked about out-of-step protection, swing rates, and then rate of change of frequency and those effects. And then IBR modeling and short circuit studies. And that is my part. So I took roughly 30 minutes. So Isabel, I'll turn it back over to you.
Thank you, Gary. So yeah, we will start the Q&A portion of the webinar. We have approximately a half hour for Q&A. So I see the questions coming in already. We have some great ones to get started with, and I will go ahead and start with some of our more narrowly scoped questions, and we'll just see how many we have time to get to. So here's one about synthetic inertia. This is from Juan Carlos Montero. And the question is simply just, what about requirements on synthetic inertia? So I think I'll pass that one off to you, Puyan.
Yeah, so, you know, that term, and there's other terms people use, emulated inertia, so on. The technologies, the wind generators certainly do that. What's in the P2800, what that is now being coined under is fast frequency response. So there is, and a lot of this is still in flux, so I don't know where it's going to land. But in the P2800, there's talk of primary frequency response and then what they right now call fast frequency response. And the fast frequency response portion, if you will, if you're like a wind turbine, you can certainly do this thing called synthetic inertia or emulated inertia, where you take some stored energy out of the rotating shaft of the machine, you burst it out into the grid, and you have to give it back. If you're a PV plant or a battery energy storage plant, then you can very quickly just put out energy because the battery has stored energy, and they'll call that fast frequency response. So P2800 is certainly taking a whack of defining those categories, if you will. The terminology may change, and still all that is in flux. As you heard Gary and I both say, that standard is not yet a standard. It's just gone through initial balloting. A lot of comments have come back, and some along those lines. And so once those comments get addressed and it solidifies, it'll get done. I hope that answers the question. If not, you can ask more clarifying questions.
Great, thank you, Puyan. This is a question that came in early on. So why not use terminologies like converter-based sources rather than inverter-based generation, or IBG, to make bidirectional power flow inclusive? That one came early on in the presentation.
Yeah, that's a very good question. So I was on another IEEE task force where we have that task force, it's a mouthful, but it's definitions of stability for converter-based generation. And in there, we call it converter-based resources. So it's as the comment came in, our thought was it's really a converter. It can go bidirectional. For some reason, other regions, NERC, even AMO, hooked onto this term inverter-based, and so it is what it is. So some people say IBR, some people say CBR or whatever. Pick your favorite term. It is what it is. I'm sorry. I hope that answers the question.
All right, thanks. So this is another one that came in more in the early part, I think, of Gary's presentation. So are these decisions to trip or not made in analog, hardware-based, or in digital, software-based?
For microprocessor relays, they are the voltages and currents are sampled by A to D converters, and so the voltages and currents are digitized, magnitude and phase angle, and the decisions are made internally with digital data, sampled digital data. I think that answers the question.
Yes,
okay.
it does. All right, so here's another one that came in. Based on the requirement for the IBR to take specific actions for three-phase and single-phase faults, one question I have, and this is from Vijay Vittal of the Arizona State University, one question I have is whether the ability to recognize the type of fault will have to be incorporated within all IBRs.
So that's a good question. Yeah, go ahead, Puyan.
No, yeah. you go first, Gary. You go first.
Yeah, I think my thinking is, and I'm certainly not speaking for the task force, I'm speaking for myself, I think the answer is yes. The IBR is going to have to recognize fault type in order to determine whether or not to produce negative sequence current or not. So the measurement of negative sequence voltage, and then which only is produced from unbalanced faults, then the negative sequence current is dependent on that. So my answer is yes, the control system will have to make that determination. We'll see if Puyon agrees or not.
Yeah, so I was going to say there's two aspects to it. So you answered the protection aspect. So I won't presume to get in that. That's not my area. But from a stability standpoint, it's not as critical to know the type of fault, but rather to know how to control voltage P and Q to remain stable and synchronized to the grid. So I think there's two aspects. So from the protection standpoint, you're the expert, Gary, and if that's what it is, that's what it is. From a stability standpoint, the distinction is not as important as being able to keep control of the three phases.
Right.
Great, thanks. All right, so here's another question that came in from Pitambar Janki. I have not seen considerations or comments in this presentation on the possibilities of using IBRs for providing compensation, harmonic compensation and VAR compensation. Does the task force discuss possibilities of compensation provided by IBRs?
So on the VAR compensation, that's inherent in voltage control. Because, you think about it, if we're talking about a SVC or a STATCOM, the intent of an SVC or STATCOM is to control voltage. So yes, it's providing reactive shunt compensation, but to control voltage. So if IBR is controlling voltage, it is inherently providing reactive compensation. So yes, that's covered in that respect. The other thing was, what was the second part of the question? Sorry, Isabel, can you repeat that? Harmonic something.
On the possibilities of using IBRs for providing compensation, harmonic compensation, and VAR compensation. Does the task force discuss these possibilities?
I'm going to assume by harmonic compensation, they mean whether you could do active harmonic filtering. And I know that has been done with things like VSC HVDC in the past. Harmonics is not my area of expertise, so I would just say maybe it's a possibility and leave it at that. Gary, do you want to add anything?
I know I can't speak to that part. So we'll have to have somebody else from the task force if we have to address that. I'm not familiar with that part.
But I can say P2800 does have a power quality section. And again, that's not my area of expertise, so I don't want to get into stuff and mess it up.
Me neither.
No problem. So here is another question that came in that seems well scoped. So regarding frequency tracking in systems with high IBR penetration, what is the proper time window, e.g. 10, 2 cycles, et cetera, for accurately detecting ROCOF? And I am not an engineer, so apologies if that's not how the acronym is pronounced.
Yeah, I'm not an expert on frequency tracking, but the way I understand it, and there's a good section in the paper about this, my understanding was that it was a one cycle window, but I could be missing something there. I'm looking here to see.
I can comment while you're looking for that.
Go ahead,
Gary.
Yeah, go ahead.
So good signal processing algorithms will typically, within 1 to 2 cycles, measure it. The thing I will offer is that with ROCOF, so ROCOF, the rate of change of frequency, this is my personal opinion, and some of this is being dialogued within P2800. I personally think that it is unadvisable to use ROCOF as an input signal to controls because rate of change of things are inherently noisy when measured in the field, and they can cause problems. It's far better to work with deadband and declines rather than rate of change. But that's just my personal view from a practical standpoint. So it's good to be able to measure it for things, like looking at even, I know ERCOT does it for some things in EMS systems, but to use it as a control signal, one has to be careful.
The only thing I'll add to this is if you're trying to measure one cycle of information and you get more based on what the frequency is, if you get more or less samples than that, then your estimation is obviously going to be wrong. So the relay, a 60 hertz relay is hoping to get 16 samples at whatever the sampling rate is. It's expecting to get 8 samples or 16 samples or whatever the sampling rate is. If it gets more or less than that, because the frequency is declining, then there are going to be errors in the filter, and then that can cause problems with whatever element in the relay is using frequency tracking. So as far as what the window should be, I can't address that. So.
All right, thanks, guys. So move on to another question here. Is there a method to calculate the ratio of synchronous generation versus IBR at which protective relays start misoperating, e.g. in a simplified system?
Yeah, I don't know of a method to do that. I think it's highly dependent on the type of system and the location and the size of the system. A much smaller system with a higher penetration may have more or less trouble. I don't know that we can put a specific ratio. The paper goes into, like I said, a few different mixes of IBR, and these are just sample systems up to between 30 and 50%, and it's expected that with that kind of percentage that the relays will actually still work properly. Generally, again, each line would have to be studied to make sure. I think my feeling is that protection engineers start to get nervous when you start talking above 50%. I think that's going to be where the issue is. I think time will tell, and we need to be studying these things. But I think above 50%, we're going to start seeing some kind of protection system problem, or at least enhancements will definitely be needed. So yeah. Yeah.
All right, thanks, Gary. It looks like this is another question for you, Gary, or this is probably for Gary. And this one's a little bit longer, so I'll read it out. If IBRs change their negative sequence currents in response to negative sequence voltage, but not their zero sequence or positive sequence currents, then they wouldn't exactly look like a synchronous machine. Is there a trade-off between emulating the traditional performance of a synchronous machine versus doing what is best for the future system needs?
Okay, that's a good question, and let's go back to conventional synchronous machines for just a minute. Many, if not most, synchronous machines that I am familiar with are high impedance grounded. The machines themselves have neutral transformers with neutral resistors, and I'm talking about generators that are connected through step-up transformers. The typical connection, at least that I am most familiar with, in North America at least, is a high impedance resistance grounded generator that's connected to the delta winding of a generator step-up transformer, and then a Y-grounded winding on the high side. So the generator itself, even a conventional synchronous generator, is not producing negative sequence current because the neutral is high resistance grounded. So that is blocking any zero sequence current that would come out of the machine. The delta winding of the step-up transformer is the other block of zero sequence current. So for conventional synchronous machines, there is no zero sequence current except what's passing through the Y-grounded neutral of the high side of the step-up transformer. So if you if you take that conventional synchronous generation and you replace it with inverter-based generation, or converter-based generation, we'll use converter, then it as long as it's producing negative sequence current, it's going to look like a synchronous generator because it's going to be producing negative sequence current, and then the zero sequence current that's coming out of the plant is coming through the Y-grounded transformer on the high side. So I think that answers the question. You can let me know if I did.
Yes, feel free to add clarification to any of your questions if I'm not reading them correctly. Right. So thanks, everyone. So we have a couple more. We're going to get to as many as we can. I think we have probably more than we'll be able to get to in the next 10 minutes. But here is another one that is on the topic of black start and recovery. So during system recovery from a big event, some IBR stakeholders can offer black start capabilities. What about the protection system marshaling or adjustments to ensure the best recovery?
I'll give that one to Puyan.
It's a very broad question. I guess it is true. There are some IBRs that provide black start capability, even in the form of grid forming inverters. I've worked on a few projects now, both in microgrids and actually grid forming converters in large grids. And they do provide those capabilities. But I think the question is very broad. Obviously, you'd have to do relay coordination, make sure everything's hunky-dory. I don't know that there's a broad answer to that question. I think you'd have to look at it on a case-by-case basis. I don't know, Gary, do you disagree?
No, I don't disagree. I don't disagree. I noticed somebody in the chat here mentioned there is a PSRC guide for black start relaying issues during black start, so that might address part of this. But
yeah.
Anyway, go ahead.
Yeah.
Sorry.
No, that's it.
Yeah.
Great. So here's one to Puyan. Could you please share some insights on small signal stability in weak grids? The possibility of bandwidth interference in this context is relatively poorly understood. What type of modeling do you suggest for root cause analysis of oscillation?
Yeah, that's a good question. I've actually recently worked on some projects on small signal stability. So there are tools out there to be commercially sensitive. I'm not going to mention them here. Most people are familiar. There are commercial tools for small signal stability. I think the issue is small signal stability models need work to be developed, and often you have to do it somewhat vendor specific. So the question is, and it's a valid question, bandwidth creep. Now you get into points where the low order oscillations, electromechanical modes may start to creep towards some oscillatory modes that may come inherently from the converter controls, the higher level controls. Well, you have to model those, otherwise you won't see that. And to model those, you need details about the control strategy, and you need to linearize those models and put them in the small signal tools. So the tools are there, but it takes some significant modeling effort to get it done. I hope that answers the question.
Thanks, Puyan. So another question, and this one may also be broad, but we'll see what you guys think. So will there not be additional burden on conventional generators under unbalanced load with increased IBR?
Not quite sure I understand what they're asking.
I will say go ahead.
I was going to say, as you get more and more penetration, the remaining synchronous generators actually start to become more and more susceptible to transient stability, because think about the case where there's only one synchronous generator left. That guy's going to fly off really quick. But I don't know about, the question was unbalanced load. I'm not sure what the thinking is there. Is that a protection issue, Gary? I don't know.
Well, that's an interesting thought. The source of unbalance in a transmission system or the source, I should say, of unbalance, primary source of unbalance in a transmission system that I'm familiar with is untransposed transmission lines. And that is a widespread issue. And of course, the higher the power transfer, the more that that manifests itself. And so I don't know if this is addressing what the questioner was asking, but if you have, depending on the changes in power flow pattern, if you retire large blocks of conventional generation in one part of the system and such that there's heavy power flow across a line that didn't used to have that kind of heavy flow, then the untransposed lines may produce, the result will be higher unbalance, which means higher negative sequence current, which means the remaining generators will have to will sense that. I would think that I don't know that that would be peculiar or in particular a problem for conventional synchronous machines. I guess the IBR would be, I think we've talked about this, the IBR control algorithms are suppressing negative sequence unless there is a high negative sequence voltage. So if the IBR are suppressing negative sequence current, the conventional synchronous machines don't have any way to suppress it. So the path for unbalance is going to be through the synchronous machines. And yes, that could be an issue. So that's kind of a long way around to think through the thought there, but I think it's possible that could be another adverse effect. Yes. So I don't know if that answers the question or not, but anyway, yeah.
Great, thanks, Gary. So I think we have time for maybe one or two more questions. So this one is related to synchronizing torque. So how can IBRs contribute to synchronizing torque to the system? And if they can't, what are the implications there?
If we think about it, converter-based generation is asynchronous, so inherently it doesn't participate in the electromechanical modes of a synchronous generator, so inherently it doesn't produce that, but it can in the same way that, for example, you can tune a power oscillation damper on a SVC STATCOM HVDC. You can indirectly induce damping and synchronizing torques on nearby synchronous generators. So there is that potential, but it depends on the location of that converter-based generation relative to large synchronous plants in the system. So that's a long way of saying there's potential, but it depends on the location of the plant. Also depends if there's a problem. So if you have a system that, another way they can impact those kind of stability issues is they'll change flows on transmission lines. They may displace large generators that had good PSSs on them. So all these things will affect damping and synchronizing torques of the existing synchronous machines. Those effects may be positive, they may be negative. So it has to be studied on a case-by-case basis. And there is potential for having a power oscillation type damper on IBR, but those are yet to be proven. I hope that answers the question. I think you're on mute, Isabel. I can't hear you.
Yes. Yep. Thanks, Kuyan. This will be our last question. So just thoughts on grid forming inverters in the absence of rotating machines. Has this been realized on a large scale at all, or is it currently still on the research level? And again, I think this will be our final question.
Yeah, so as I said, I've worked on a few projects in microgrids and large grids. So they are coming. There are vendors that will supply grid forming converters today, but applications on large scale, the answer is no. I mean, there's no grid to my knowledge where you can say, 50% of the IBR today is grid forming. So I think there's a lot of R&D to be had. And just the whole concept of grid forming right now there's no one concept. There's probably half a dozen different concepts. And so which one will show the most promise, or whether it'll be all that get applied, all these things remain to be seen. There's still much R&D, but there's great potential in it. I don't know from a protection standpoint, Gary, if you want to add anything.
No, I really can't. We do have a one of the attendees here in the chat window mentions this black start issue associated with or protection issues associated with black start, the report coming out, but I don't think it addresses grid forming. So I'm not aware of work in that area yet, at least as far as conventional system protection. So I can't add anything to it.
Great. Well, we are at the half hour. I will just take a moment here to thank Gary and Puyan for speaking today. That was a great presentation. I'll remind all of the attendees that we will send a follow-up email to you with a link to the recording and other materials. Thanks to IEEE for helping put this together. And again, if you would like to learn more about the Global Power System Transformation Consortium or review any of the other resources we have available, please visit our website at globalpst.org. And thanks again, everyone, for joining us today. We'll go ahead and conclude the webinar now.
Can I make one last comment? Just wanted to thank Isabel
of course.
And everybody in the background that did tremendous amount of work to make this all happen. So thank you very much.
Thank you, Puyan. I appreciate that. All right, everyone. Thanks again for joining us, and have a wonderful night, morning, afternoon, wherever you're at. Have a wonderful day. Thanks, everyone.